Dear students, starting chapter 1, relation and function. First topic is relation and types of relation. In class 11th, you learn about a relation. We know that if A is any non-empty set, as for example, if I take to understand terminology in definition, here I am taking one parallel example, that I am taking a set containing three numbers 1, 2, 3. Then A cross A, it contains 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. So A has 3 elements. A cross A has 9 elements. Here A has 3 elements. So A cross A has 9 elements. 3 into 3, 3 square elements. Now, if we find subsets of A cross A, then total number of subsets of A cross A is 2 raised to, if any set has n elements, then its number of subsets is 2 raised to n. That is 2 raised to 9. It is 2 raised to 9. 512 subsets. And every subset of A cross A, or if you select any subset from these 512 subsets, then any subset is said to be a relation in set A. Any subset in A cross A, any subset of A cross A is said to be a relation in set A. See here, we can prepare total of 512 subsets. If we keep list of subsets, as for example, if we prepare list of subsets, then we can prepare 512 subsets. We know that null set is subset of A cross A. Set itself is subset of A cross A. If we take, suppose 1, 1, 1, 2, 1, 3, I am taking only these 3 elements. This is a subset of A cross A. If we take, suppose 1, 1, 2, 2, 3, 3, 3, 2, 2, 3, this is a subset of A cross A. So if we prepare a list of 512 subsets, then this subset has no elements. There are some subsets containing single element. There will be some subsets containing 2 elements. This subset is containing 3 elements. This subset is containing 5 elements. This is containing 9 elements. So we can prepare a list of 512 subsets. And every subset of A cross A, is said to be a relation in set A. So these all are relations in set A. So we have 512 relations in this set A. So I am putting these words here in definition. Let A be non-empty set. Then any subset of A cross A is said to be a relation in set A if A has n elements. If A has n elements, then number of relations, total number of relations in set A, it is equal to total number of subsets of A cross A, and it is equal to 2 raised to n square, because A cross A has n square elements. So keep remember this formula. Now we discuss types of relation. Types of relation. First type is reflexive relation. Reflexive relation. See, explaining words using a definition. Suppose from this 512 relations, so here these definitions I am explaining by this example. Using same example, I am explaining definitions, types of relations. Reflexive relation. Suppose here we take a relation, taking relation R. Suppose relation R, that means any subset, any member from this family. There are 512 subsets. I am taking any one subset here, which I am calling R. Relations are denoted by R. Relations are denoted by R or sometimes S. Maximum it is denoted by R. First letter of word relation. Suppose I am taking one relation. Relation means subset of A cross A. So selecting one subset. Suppose I take 1 1 2 1 2 2 3 2 2 3 3. I am taking here 2 2 2 3 3 3. See, this subset of R, subset of A cross A contains 1 2 3 4 5 elements. It is a subset of A cross A, hence it is a relation. It is a relation in set A. Now look here. See, A has these 3 elements. 1 2 3. First of all, take 1. Check in this relation. See, for 1, its doubling is here 1 1. Take 2. For 2, its doubling is here 2 2. 3, its doubling is here 3 3. Doubling of every element of set A is included in this relation. no one, doubling of no one is left, doubling of every element is included. So in given relation, doubling of every element must exist, then it is said to be a reflexive relation. It is a reflexive relation. It is a reflexive relation. In given set A, because for every element, let me say A, every element belonging to A, so this word is very important, every A belonging to relation R. Let me take one more example. Suppose if we take R, suppose I am taking 1 1 1 2 2 2 2 3 3 1. Now look here, 1, doubling of 1 is here, 1 1. Take 2, doubling of 2 is here, 2 2. Check for 3, doubling of 3 does not belong to this set. So doubling of 3 is left. So this is not a reflexive relation. So this relation is not a reflexive relation in R, because 3 belongs to A, but 3 3 does not belong to R. So this word is very important. Every A belonging to A, its doubling must be in R. So here I am putting now words that for every A belonging to A, if A belonging to R, then R is said to be a reflexive relation in given set A. So this is the meaning of reflexive relation. Second type, a symmetric relation. To understand this word, again I am taking same example. Let me take A. We are taking same set A containing 1 2 3. Now here, if we take relation R, then R, suppose I am taking 1 1 1 3 2 2 2 3, then 1 1 1 3 2 2 2 3 3 1. Let me take these 4 elements, 1 1 1 3 2 2 2 3 3 1. Let me include one more, 3 2. See, we can make a list of 512 subsets. 512 subsets of A cross A. This is a subset of A cross A. So here, if we take this R, then it is a relation in given set A. It is a one relation. It is a subset of A cross A. Now look here. I have taken this example to explain this word symmetric relation. So here, now to check symmetric relation, observe every element of relation R. Say 1 1, say here 1 1 is in R, then take its inverse. Inverse is 1 1. Say I am saying inverse of AB is BA. Inverse of AB is BA. So if AB is in R, check BA. So 1 1 is in R, 1 1 its inverse itself, so belongs to R. 1 3, then its inverse is 3 1. Here it is 3 1. It belongs to R. Take next 2 2. Its inverse is 2 2. It belongs to R. 2 3. So its inverse 3 2. So 3 2 is here. Say. Take 3 1. 3 1. Its inverse is already discussed. 1 3. 3 2. Its inverse is 2 3. So see here what is happening. Every ordered pair EB belonging to R, here every EB belonging to R, for every ordered pair AB belonging to R, BA also belongs to R. AB belonging to R implies BA belonging to R. So here we can put this statement by this method using implication, that AB belonging to R, AB belonging to R implies BA belonging to R. If this condition is satisfied, say it should be for every AB belonging to R. It must be true for every such ordered pair belonging to R. Therefore, R is a symmetric relation. We check this property for every ordered pair belonging to relation R. Suppose I am taking one more example. Suppose I take R is equal to 1 1, 1 2, 1 3, then 2 2, 3 1. This is a relation in R. It is a relation in set A. Given set A, it is a relation in set A. Now see, 1 1, its inverse is 1 1 itself, so belongs to R. Now check next, 1 2, its inverse is 2 1. See, find out 2 1, where 2 1 belongs in this set. So 2 1, nowhere is 2 1. So for 1 2, there is a problem. Its inverse does not belong to R. Check next, 1 3, 3 1, it belongs to R. 2 2, its inverse is 2 2. 3 1, its inverse is 1 3. For other order pairs, it is happening. But for this order pair, its inverse does not belong to R. So if you find at least one order pair EB in given relation R, for which if its inverse BA does not belong to R, then that relation is not symmetric. If any relation containing 100 elements, 100 order pairs, for 100 order pairs, if out of 100 ordered pairs, if 99 are satisfying this condition, EB belonging to R implies BA belonging to R. But if you find at least one element whose inverse does not belong to R, then it is not said to be symmetric relation. So here what is happening, 1 2 belonging to R, but 2 1 does not belong to R. if you find at least one such element in given relation, then it is not a symmetric relation. Therefore, R is not a symmetric relation. Condition is that for every element of given relation, this should be true. So here I am putting word. For every AB belonging to given relation, here what is R? R is a relation in set A. Let R be a relation in set A. If for every AB belonging to R, check for every ordered pair in R, AB belonging to R implies BA belonging to R. If this condition is satisfied, then given relation R is said to be a symmetric relation. So this is the meaning of symmetric relation. Now third topic is transitive relation. Transitive relation. To understand this word, again I am taking example. Suppose example is, let A be set containing, we are taking same example to understand these words, 1, 2, 3. Now I take first example, R is equal to, means I am taking a subset of A cross A. So it will be relation in set A. So say here I am taking 1, 1, 1, 2, then 2, 1, 3, 1, 3, 2. Suppose I am taking these elements 1, 1, 1, 2, 2, 1, 3, 1, 3, 2. So let me take these elements. This is a relation. It is a relation in R. Sorry, a relation in set A. Now what we will check for transitivity? Say in this relation we shall find all those elements. We shall find a pair of elements. Pair of elements means two elements, such that AB is in R and BC is in R. AB is in R, BC is in R. So we shall find such type of elements in which B is in common. This number is in common. Implies then what we need? We need AC belonging to R. For all such type of elements belonging to R, AC must be belonging to R. Then this relation is said to be transitive relation. So see, let me check. Say here 1, 1 and 1, 2, in which 1 is in common. Say 1, 1 and 1, 2, both are belonging to R. Take from this set only. in which B is in common. See, consider this as B, AB, BC. Now what we want? We want AC. Does 1, 2 belonging to R? It is here. Already 1, 2 belonging to R. So it is in R. Now we check for second pair of such elements. Suppose I am taking here 1, 1, then there is no any other elements in which first place has 1. Now let me take 1, 2, 2, 1. See, 1, 2, 2, 1. So 2 is in common. So what we want? We have to find out 1, 1. Does 1, 1 belonging to R? So check here. It is here. Yes, this is in R. We check. Suppose I take here 3, 1, 3, 1, 1, 2, 3, 1, 1, 2, 3, 1. See, 3, 1 is on the right side, 1, 2 is on left side. Whenever you selected two elements, it does not mean that first element is always from left side, second element from right side. So in this pair, 3, 1 is on right side and 1, 2 is on left side. So keep your observation perfect. No any such pair of elements must be left from your observation in which B is in common. So here B is in common. Now what we want? We need 3, 2. 3, 2 belonging to R. Now does it belonging to R? Check here. So here it is 3, 2. 3, 2 already it is in R. Yes, 3, 2 belongs to R. Check for other. Suppose this is 2, 1. 2, 1, 1, 2. 2, 1, 1, 2. Say 2, 1. 1, 2. 2, 1 is on right side, 1, 2 is on left side. So if I arrange by this way, 2, 1, 1, 2. See, previously what we had taken? 1, 2, 2, 1. See, here I had taken 1, 2, 2, 1. In which 2 was in common. Now I am taking 2, 1, 1, 2. So see, 1 is in common. 1 is in common. Satisfying this condition, B must be in common. This is common. Now what we want? 2, 2. Does 2, 2 belonging to R? Check here. See, 2, 2 does not belong to R. Nowhere 2, 2 in this set. So 2, 2 does not belong to R. So for this ordered pair, for this pair of elements, condition is broken. This is broken. So this relation is not symmetric relation. If you find at least one pair of such elements which does not belong to R, for which AC does not belong to R, it is not symmetric. But if in this set, if I include suppose 2, 2, suppose here somewhere I include 2, 2, then it will be transitive relation. Suppose I am adding here 2, 2. One more element I am adding to make it symmetric. I am adding 2, 2. Suppose after 2, 1. Now I have changed this relation. So say 2, 1, now 2, 2. 2, 2 is in R. As I added, 2, 2 is in R. Check for other. 3, 1, 1, 2. 3, see, already discussed. 3, 1, 1, 2, we have discussed. Now 3, 2, 2, 2. See, 3, 2, 2 2. 3 2 2 2, in which 2 is in common. So we have to check for 3 2. Does it belong to R? So yes, it is this one. It is in R. So I think for every ordered pairs, for every pair of such elements in which B is in common, AC is in R. Here these converts are satisfied. So this is transitive relation. It is a transitive relation. This relation, a transitive relation, because for every AB and BC belonging to R in which this is common, we have AC also belonging to R. Therefore, this is a transitive relation. So now I am here putting words. Let R be a relation in set A if for all AB and BC belonging to R, AB belong to R and BC belong to R implies AC belonging to R. Or in short, this can be written as putting this in little short way, let R be a relation in A if for all AB and BC belonging to R, if AB belonging to R, BC belonging to R, or for all AB and BC belonging to R. Okay, it will do. For all AB, BC belonging to R in which B is in common, if AC belonging to R, then, so this is conditional statement. Then relation R is said to be a transitive relation. And when it is not transitive, if we can find AB and BC belonging to R in which B is in common, this element common, but if AC does not belong to R, then R is not a transitive relation. It is not a transitive relation. So here this is example for transitive relation. Now as discussed, if I remove this last element 3 2, if I remove this 3 2, here I am removing 3 2. So second, if R is equal to 1 1 1 2 2 1 2 2 3 1 1 1 1 2 2 1 2 2 3 1. Now I do not include 3 2. So see here, this will be satisfied. As discussed, all statements are true. 3 2, okay, this will not also be true. Here 3 1 3 1 is in R. 3 1 is in R. 1 2 is in R. But 3 2 does not belong to R. So therefore this is not transitive relation. Whenever you find such pair of elements in which AB is in R, BC is in R, but AC does not belong to R. If you find such 100 pair of elements satisfying this condition, but if you find at least one pair of such elements, if there are such 99 statements true, similar 99 statements are true, but if you find at least one statement not true, means not belonging to R, then it is not transitive relation. So here we put a reason. This is R is not a transitive relation because condition is true for a few pair of elements but not true for all pair of such elements in which B is in common. There exists a pair of elements in which B is in common, condition is not satisfied. So reason is the relation is not a transitive relation because 3 1 belonging to R and 1 2 belonging to R, but 3 2 does not belonging to R. So say AB belonging to R, BC belonging to R, but AC does not belonging to R. Therefore this element R is not a transitive relation. Let me take one more example. Suppose if we I take a relation R is equal to, if relation includes 1 1 2 2 3 3, I take these three elements 1 1 2 2 3 3. This is a relation in set A. It is a relation in set A. This was also a relation in set A, and this is not transitive. Here one more relation in set A. It is a relation in set A. Now we check properties. First property was reflexive. For reflexive, what we check? Doubling of every element of set A. See, doubling of 1 is there, doubling of 2 is there, doubling of 3 is there, doubling of every element is there. So we say for every A belonging to R, every A belonging to set A, not R. Every A belonging to set A belonging to R, therefore R is a reflexive relation. Then next word was symmetric. For symmetric, what we check? For symmetric, we check in the given relation. We pick every element of R. What is required? Inverse of every must be in same set. Say inverse of 1 1. It is 1 1 itself. Inverse of 2 2 is 2 2. Inverse of 3 3 is 3 3. Means inverse of AB is BA itself. So it is symmetric. So here for every AB belonging to R, we have BA belonging to R. So R is symmetric. Therefore, R is a symmetric relation. Now very important statement, third statement. This is transitive. If AB and BC belonging to R implies AC belonging to R. But if you find at least a pair of elements in which B is in common, if AC does not belong to R, then it is not transitive. Say here, these are words. What is, see, this is conditional statement. You have to find B is in common. Find such a pair of elements. If you can find such a pair of elements in which B is in common, then check existence of AC. It is conditional statement. First requirement is B common. Then if you find B common and AC does not belong to R, then it is not a transitive relation. So existence of AB and BC is must to check this property. So say here, find out such a pair of elements AB and BC in which B is in common. Say if you check these two, so here these elements are not in common. If you check for these two, this element is not in common. If you check for these two, this element is not in common. If you find common element and AC does not belong to R, then it is said to be not a transitive. See, look here. If you find pair of elements in which B is in common but 3, 2 does not belong to R, then it is not transitive. So this existence is must to check this property. But because here no existence of such pair of elements, so no question of existence of AC. So by logic, what we say here, by logic, this condition is satisfied, that we can say. So here by logic, it is clear that EB belonging to R and BC belonging to R implies AC belonging to R. By logic, this is satisfied. So I am putting this word by logic. Therefore, this relation is a transitive relation. Say in short, you remember one trick. If you are given 1, 2, 3 and the relation contains 1, 1, 2, 2, 3, 3, 1, 1, 2, 2, 3, 3, then it is a symmetric, it is reflexive, but it is symmetric, it is reflexive, and it is transitive. It is all, it satisfies all properties. If you are given here 4 numbers 1, 2, 3, 4, and here if you are given 1, 1, 2, 2, 3, 3, 4, 4, then it satisfies all 3 properties. It is symmetric, it is reflexive, it is transitive. If here you are given 10 elements 1 to 10 and set R relation contains 10 ordered pairs, doubling of each one, means 1, 1, 2, 2, 3, 3, 4, 4, 10, 10. Then it is again, it is transitive, it is reflexive, it is symmetric. Suppose fourth relation, say here we are discussing on this set. If we take R, suppose I am taking 1, 1 and 2, 2. This is a subset of A cross A, so it is a relation in set A. Now check property. Is it reflexive. So see, for reflexivity, check every element of a given set A. 1, its doubling is here. 2, its doubling is here, but doubling of 3 is missed. No doubling of 3. So this is not reflexive. So here R is not reflexive because 3 belongs to A, but 3 does not belong to R. For every element of set A, its doubling must be in R, then it is said to be reflexive. Second property, is it symmetric? For symmetricity, check a relation. Check every element of relation. Inverse of every element must be in itself. Say inverse of 1 1, it is in R itself. Inverse of 2 2 is 2 2. Inverse of AB is BA. For every AB belonging to R, if you find BA belonging to R, then it is symmetric. So here R is symmetric. Because for every AB belonging to R, we have its inverse BA belonging to R, so it is symmetric. Now is it reflexive? So as just discussed in example 3, here there is no existence of at least a pair of elements in which B is in common. So by logic, this is transitive. Here R is transitive because by logic EB belonging to R and BC belonging to R implies AC belonging to R. This property is satisfied. This is transitive. So this relation is symmetric, transitive, but not reflexive. Now, type of relation, that is equivalence relation, type 4. Equivalence relation means if any relation is reflexive, symmetric and transitive, it is said to be an equivalence relation. So if any relation is reflexive, it is symmetric and transitive, satisfying all these three words, then it is said to be equivalence relation. As for example, let me take, if we take R, we are discussing on same set A. Suppose I take 1 1 1 2 2 1 2 2 3 1 3 3. Let me check elements. 2 1 3 1 3 3 3 1 2 1 1 2 2 2. What I want to explain, for which I am verifying elements. If requires, I will add, otherwise I will keep closed. 1 1 1 2 1 1 2 1 1 1 2 1 2 2 3 1 3 3 1 3. I include here 1 3. Suppose including 1 3. 1 3 2 1 2 2 3 1 3 3. 1 3 3 1 3 1 1 3 3 3 2 2 1 2. Okay, let me check for this relation. See, on in every ordered pair, first entry and second entry, both entries are in set A, then it is a relation in set A. This is a relation in set A, explaining the meaning of equivalence relation. Now, to check equivalence relation, we have to check these three properties: reflexive, symmetric and transitive. First of all, reflexive. For reflexive, say here this is a relation in set A. A is 1 2 3. Now, to check reflexivity, observe set A. See, every element of given set A, its doubling must be in relation R. See, first of all, 1. Here 1 1 is in R. 2, here 2 2 is in R. For 3, 3 3 is in R. So for every A belonging to set A, its doubling is in R. Therefore, R is a reflexive relation. So first word is satisfied. For reflexivity, every element of given set, its doubling must be in R. Now to check symmetricity, is it symmetric? Then check every ordered pair in given relation. If AB is in R, BA must be in R. So see, 1 1 is in R. So its inverse is 1 1. 1 2, its inverse is 2 1. 1 3, its inverse is 3 1. 2 1, its inverse is 1 2. 2 2, its inverse is itself. 3 1, its inverse is 1 3. 3 3, its inverse is 3 3. AB, then check for BA. A PQ, check for QP. So here, satisfied. So this is symmetric relation. So for every AB belonging to R, we have BA belonging to R. Therefore, R is symmetric. Now third property, transitivity. Say, for transitivity what we check? AB and for all those elements in which B is in common, pair of elements in which B is in common, AC must be in R. So say here 1 1 1 2. See, 1 is common. So check for 1 2. Say here 1 1 1 2. 1 is in common. So check for 1 2. Does 1 2 belonging to R? So 1 2, yes, it is here 1 2. Now check 1 1 1 3. Check for this 2. 1 1 1 3. See, no one should be left. So 1 is in common. So 1 3, it is in R. 1 3. Then we take next pair of elements in which B is in common. Suppose we take 2 1 1 3. See, look here, 2 1 1 3. 2 1 1 3. Then we want 2 3. Now does 2 3 belonging to R? No, 2 3 is in R. So here on this step, on this selection, condition is broken. no need to go ahead. Don't check for other pair of elements. As you get a pair of elements in having B in common, if AC does not belong to R, then it is not transitive. So to make it transitive, I have to add 2, 3 in this set. Suppose I add 2, 3. Suppose here, if I add 2, 3, then what will happen? To be symmetric, 3, 2 must be in this set. So here, taking 2, 3, this will be in R. But then this condition will be broken, because if we add 2, 3 belonging to R, then 3, 2 does not belonging to R. So then it will not be symmetric. So this is the way of checking for elements. So if we don't add 2, 3, then this is not in R. So this is not transitive. So here, if not transitive, give example. If not reflexive, give example. If not symmetric, give that counter example. Here 2, 1 and 1, 3 belonging to R. 2, 1 and 1, 3. 2, 1 and 1, 3. 1 is in common. Say this, observe this element on left. Observe this element on right side. Left, right. Then you will see common. Otherwise, if you will observe as they are, then you can't find here common. So you have to shuffle in every direction. Pair of elements, you have to shuffle in both directions, left, right, right, left. Then you can find. Otherwise, there may be possibility of mistake if any such a pair of element is skipped without observation. So 2, 1, 1, 3 is in R. But 2, 3 does not belong to R, therefore this is not transitive. So because all three words are not satisfied, this is not an equivalence relation. If any relation is reflexive, symmetric and transitive, then it is equivalence. But here this third word is not satisfied, therefore this relation is not equivalence relation. If it was transitive, then it is equivalence relation. Is a relation R in the set A? So given set contains first 14 natural numbers and the relation is defined by this set. Is it a reflexive, a symmetric or transitive? That is the question. So here set A contains first 14 natural numbers and R is a relation containing all those ordered pairs satisfying 3x minus y equal to 0. That means it is set of all our ordered pairs such that y equal to 3x. That means it is set of all ordered pairs in which value of y is 3x. And say here x is in set A. See, both numbers x and 3x must be from A. Then and only then it will be a relation. So this can be expressed by this way. So this is a relation in set A. Now let me put list of elements. So R is equal to, say, x. If I take x equal to 1, then this will be 3. If I take x equal to 2, this will be 6. If I keep x equal to 3, this will be 9. If x is 4, this will be 12. If x is 5, this will be 15. But say, this is a relation in A. So this set must be subset of A cross A. Means both elements in first place as well as in second place, both elements must be belonging to A. But now 5 onwards, what is happening? 5 is in A, but 15 does not belong to A. So this is not allowed. If you take here 6, then second element will be 18. So 6, 18. 18 is not in this set. 6 is there, but 18 is not there. So 6, 18. This is not allowed. Because this is a subset of A cross A, both entries must be in A, and A contains maximum 14. So don't include these elements. So these are only the elements in a relation R. Now we check one by one. Is it reflexive? So for reflexivity, every elements of set A, doubling of every element of set A must be in R. See, first element is 1. Check, does 1 1 belong to this set? So you can see that 1 1, no 1 1, no 2 2, no 3 3, no doubling of any element. So this is not reflexive. So 1 belonging to A, but 1 1 does not belong into R. Condition is not satisfied for very first elements, so no need to check for second, third onwards. If you find at least one element whose doubling is not in R, so R is not, this is not reflexive. Second property, symmetric. Is it symmetric? For symmetricity, we check from relation R. Take every ordered pair one by one. If AB is in R, BA must be in R. See, AB 1 3. So its inverse is 3 1. No 3 1 is here. So condition is broken. So here 1 3 belongs to R, but 3 1 does not belong to R. So by checking from first element, this is not satisfied, so no need to go ahead. If condition is true for first element, go for second. Check for second. If it is true, check for third. Wherever condition is broken, no need to go ahead. So here this is not satisfied, therefore R is not symmetric. Third is transitivity. Find out pair of elements in which B is in common, and if you find AC does not belong to R, it is not transitive. So say here, this is 1 3, 1 3, here 3 1. So 1 3 is in R and 3 9 is in R. Now check for 1 9. See, this is common. This element is common. Now check for 1 9. Does 1 9 belong to R? No. AB is in R and BC is in R, but AC does not belong to R. If you find at least one pair of such elements, then don't check for others. So this is not transitive. So R is not a transitive relation. So this is not reflexive, it is not symmetric, it is not transitive. Now this side, this question is R in set A defined as y is divisible by x, a reflexive, a symmetric, or a transitive? Say here, set A is 1, 2, 3, 4, 5, 6. R is x, y such that y is divisible by x. Y is divisible by x means x divides y. Let me put in more simple form. This means what? X divides y, because we are putting a value of x first, then we keep y. So for convenience in finding elements, we are changing these words. Now x, both x and y must be from A. Suppose I put here 1. Now 1 divides y. So 1 divides 1, 1 divides 2, 1 divides 3, 1 divides 4, 1 divides 5, 1 divides 6. Now I take here x equal to 2. Then say 2 does not divide 1. So 2, 1 is not allowed. 2 divides 2. 2 does not divide 3. 2 divides 4. 2 divides 6. Then take 3. 3 does not divide 1. 3 does not divide 2. 3 does not divide 4. 3 does not divide 5. 3 divides 6. 3 divides 6. Then take 4. 4 does not divide 5. 4 does not divide 6. Say here we have missed one element. 3 divides 3. 3 divides 3. 3 divides 6. Then 4 divides 4. 4 does not divide 5. 4 does not divide 6. Then 5 divides 5. Don't miss A. Doubling. 5 divides 5. So 5 belongs to R. 5 does not divide 6. Then 6 divides 6. So these are elements satisfying this condition. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 elements. Now we check one by one. So we check properties one by one. First property, reflexivity. For reflexivity, observe given set A. Say always keep remember, when we check reflexivity, observe A. When we check symmetricity and transitivity, then look in R. For symmetricity and transitivity, look in R. But when you check reflexivity, look in A. Because every element of A, its doubling we require. See, doubling of 1. So 1, 1 is here. Doubling of 2, 2, 2 is here. Doubling of 3, 3, 3 is here. Doubling of 4, 4, 4 is here. Doubling of 5 is here. Doubling of 6 is here. Doubling of everyone is here. Because A divides A. So this we keep by this way. See here, first property, that for every A belonging to A divides A. A divides A. A divides A. A divides A. For every A belonging to A divides A. Therefore, A belonging to R. So R is reflexive. Now we check symmetricity. See, for symmetricity, look in R. See, 1 2 is in R, but 2 1 is not in R. Sufficient to say that it is not symmetric. 1 2 belonging to R, but 2 1 does not belong into R. Therefore, this is not symmetric. Third property for transitivity. For transitivity, say here property is x divides y. See, transitivity can also be explained. For this example, we can also explain by this way, that say if you observe practically, then what happens? 1 2 is in R and 2 4 is in also R. 1 2 2 4. See, 2 is common. Now check for 1 4. It is here 1 4. See here 1 3 is in R, 3 6 is in R. 1 3 3 6, 3 is in common. So 1 6 is also in R. Here it will be true, because from these properties it is clear that if A divides B and if B divides C, then A divides C. So let me put these words by this method, that let AB belonging to R and BC belonging to R. AB is in R, BC is in R, in which B is in common. Like this, 1 3 belongs to R, 3 6 belongs to R. So in which 3 is in common. So statements are for all those such a pair of elements in which B is in common. This means A divides B and this means B divides C. Now A divides B. If A divides B, then A is a factor of B. So B can be expressed as something into A, M into A. If A divides B, then A is a factor of B. So in B there is a factor A, and B divides C means B is a factor of C. So C is equal to N into B, where Mn are some natural numbers. Mn are integers such that B and C belonging to A. So let me put M and N are integers, natural numbers. Okay. M and N are natural numbers such that B, C both must be in set A. Not any natural numbers. Take those natural numbers for which B and C values should be in A. Now this value I am putting here. So B is equal to C is equal to N into, now putting B equal to MA. So that is C is equal to Mn into A, where M is a natural number, N is a natural number, so Mn is a new natural number. So what it proves? It proves that A divides C. A is a factor of C. This means A is a factor of C. So A divides C. So AC belonging to R. AC belonging to R. Therefore, R is a transitive relation. relation are in the set Z of all integers defined as R is equal to set of ordered pairs xy such that x minus y is an integer. Is it a reflexive, symmetric or a transitive? Say here R is set of ordered pairs xy such that x minus y is an integer. It is relation. It is a relation in set Z of integers. Now we check properties one by one. See, first property, to check reflexivity, we check for every element of a set on which a relation is defined. See, for every, if we take any element A from Z, if you take any element from Z, then A minus A, it is 0. This is equal to 0. Obviously, it is an integer. So A minus A, it is equal to 0. It is an integer. So A minus A is an integer. So A belongs to R. Therefore, A belonging to R. So for every A belonging to Z, its doubling is in R. Means 1 belongs to R, 2 belongs to R, 3 belongs to R, 4 belongs to R, like that. So therefore R is a reflexive relation. Second property, symmetricity. For symmetricity, we take any element from this set R. See, for any, we take any element EB belonging to R. This is any element. AB is in R. So I put here word for every. For every AB belonging to R. If AB is in R, it happens if A minus B is an integer. So it happens if A minus B is an integer. This means difference will be integer. If A minus B is integer, then B minus A is also an integer. It is always true. And if B minus A is an integer, then BA belongs to R. So therefore BA belonging to R. So therefore R is a symmetric relation. Third property. In third property, what we do? We take all those elements for which AB is in R and BC is in R, and we want to check is AC in R, that we want to check. So checking for all those pair of elements in which B is in common. So if AB is in R, BC is in R, does AC belong to R? So let we check. If AB is in R, then obviously A minus B is an integer. This is an integer, and if BC belongs to R, BC belonging to R, then B minus C is also an integer. B minus C is also an integer. A minus B is an integer, B minus C is an integer. So sum of two integers is again a new integer. So this is also an integer. That means what is proved? AC belonging to R. AC is an integer. AC, A minus, this will be cancelled. So a minus c is an integer, and a minus c is an integer, that means AC belonging to R. So this is proved. Say we began from AB belong to R, BC belong to R, and what is proved? AC belonging to R. So therefore relation R is a transitive relation. It is a transitive relation. Now in this question, say here, A contains a human being in a town, and R is a relation such that X is exactly 7 centimeter taller than Y. This is a pair of two persons. Pair of two persons are belonging to such ordered pairs belonging to R. If first one is exactly 7 centimeter taller than second person, first person must be exactly 7 centimeter taller than second person, then pair of those two persons belonging to R, that ordered pair belonging to R. So R contains a set of such all ordered pairs, and this is a relation. It is a relation in the set A of human being in a town at a particular time. Time is particular. In a town at a particular time. Now let me check properties. Say AA belonging to R. When AA belonging to R can be said if A is exactly 7 centimeter taller than A. Any person is exactly 7 centimeter taller than itself. Not possible. How it is possible that anyone is 7 centimeter taller than himself only? It is not possible. So any person A is exactly 7 centimeter taller than himself, him or herself, is not possible. So AA does not belong to R. So R is not reflexive. R is not reflexive. Second property, symmetricity. Let AB belonging to R. Suppose we take any element from R. If AB belonging to R, that means A is exactly 7 centimeter taller than B. That means A is exactly 7 centimeter taller than B. That means B is smaller than A. A is taller than B, B is smaller than A. So that means B is not taller than who is taller? A is taller than B, not B is taller. So BA does not belong to R. BA does not belong to R. So R is not symmetric. Therefore, R is not symmetric relation. Third property. Suppose that AB belonging to R and BC belonging to R. I have taken B common. This person is common. This is same person. This means what? That A is exactly 7 centimeter taller than B, and B is exactly 7 centimeter taller than C. A is taller than B. B is taller than C. Each one by 7 centimeter, 7 centimeter. That means what? A is exactly 14 centimeter taller than C. If A is 7 centimeter taller, then it belongs to R. But here A is 14 centimeter taller than C. So AC does not belong to R. So say AB is in R, BC is in R, but AC does not belong to R. So R is not a transitive relation. Say here, this is a relation. Relation is set of all AB such that A is less than or equal to B square. It is a relation in set of real numbers. Say this is set of real numbers. Symbol is differed by this double line. This symbol is for set of real numbers, and here this symbol is for relation. So don't be confused in these symbols. This is set of real numbers. This is set a relation. Now we check these words: reflexive, symmetric, transitive. Say A less than or equal to B square. If you check this for any integer, then what will happen? If you check here for 1 less than or equal to 1 square, it is true. So 1 belongs to R. Say 2 is less than or equal to 2 square. 2 is less than or equal to 2 square, so 2 belongs to R. 3 is less than or equal to 3 square. So 3 belongs to R. So if you check for integers, if these are integers, if you take here negative, -3 less than or equal to -3 square, this is also true. -3 less than or equal to -3 square, so -3 belongs to R. So you can see that by observing this examples, you can see that A is coming in R. So from first observation, you can imagine, you can say that this is reflexive because doubling belongs to R. But see here, relation is in set of real numbers. So if I take here 0.4, see if keep here 0.4, 0.4 and here 0.4 square, which is smaller? This is 0.16. 0.16 is smaller than 0.4. So this is not less than or equal to this number. So if you select any number, if you take 0.3, 0.3, 0.4, 0.4, then this numbers may not belong into R. So don't consider your integers. If you consider integers, then you will do mistake that it is reflexive. But if you think about a non-integer number, and we have to check for every real number. R is set of real numbers. So don't miss to think about any real. Don't think about integers. R is set of all real numbers and this is real. So taking 0.4 from this set, this condition is not satisfied. Therefore 0.4, 0.4 does not belong to R. And only one such example is sufficient to say that this relation is not reflexive. It is not a reflexive. Now we check second word. Second word, that is symmetricity. See, if I take here 1 A1 B, suppose I take 7 square. 1 is less than or equal to 7 square is true. This is true. That means 1 7 belongs to R. But does 7 1 belong to R? We want to check this. 1 7 belong to R. Does 7 1 belong to R? When we can say 7 1 belongs to R? If 7 less than 1 square. Is 7 less than 1 square? This is not true. 7 is not less than or equal to 1 square. So this is true. But 7 is not less than 1 square. Therefore 1 7 belongs to R, but 7 1 does not belong to R. So this example is sufficient to say that R is not symmetric. Now transitivity. For transitivity, we have to think a number, two numbers AB, two elements in which B in common belonging to R, such that does AC belonging to R, that we have to check. If this is not satisfied, it is not transitive. Here also you have to take numbers by trick. So try to find out two ordered pairs in which B common belonging to R, but AC does not belong to R. See, if I take here, say taking way by trick, I am taking one positive, one negative. Say if I take 4 and here minus 3, 4 B minus 3. This is true. 4 is less than minus 3 square. It is true. That means 4 minus 3 belonging to R. And now I am taking putting minus 3 common. See, minus 3 common. This number I am taking common. Now selection of second number by trick. Minus 3 square less than or equal to, sorry, here we keep minus 3, not square, left side we keep this number, minus 3 less than or equal to. Now see, if I keep here 1 square, this is true. So minus 3 1 belongs to R. But say here 4 1, does 4 1 belonging to R? 4 1 belonging to R if 4 less than or equal to 1 square. But 4 1 does not belong to R because here 4 less than or equal to 1 square, this is not true. 4 less than or equal to minus 3 square and minus 3 less than 1 square, but 4 is not less than to 1 square implies 4 1 does not belong to R. So what is proved here? Thus 4 minus 3 belonging to R, or we can put this in one line, that is, these are true, but 4 not less than or equal to 1 square. So this is true, but 4 1 does not belong to R. Therefore, this relation, R is not a transitive relation.